So what's amazing about this problem is how many different topics are included. One problem. Let's look at it and see what we know and see what we can do. So we've got a satellite, real world problem. We've got a satellite circling the Earth. It's about 200 miles above the Earth. Satellites generally are between 150 and 250. Some of them are higher, some of them are lower. Okay, it must be in constant direct contact with a tracking station on Earth. Not all satellites need this, but we're creating this kind of satellite. So it must always be in contact with a tracking station. What is the maximum distance on the Earth's surface that can be between the tracking stations? We're going to ignore political boundaries. We're going to ignore geographic challenges. We're just going to say, what is that distance on the Earth? You'll need, the radius of the Earth is 3,960 miles. So let's actually start by drawing a picture together. We're going to work through this at different stages. So please note, this is not to scale, but I've drawn this arc represents the Earth, the surface of the Earth. Here's the satellite, which is going to maintain a 200-mile height above the surface of the Earth, and it's going to stay constant. So we're going to say, okay, it's going to travel in a roughly circular orbit here. This is the radius of the Earth, 3,960 miles. So you can see this distance from the satellite to the center of the Earth is 3,960 plus 200. Now the question is, clearly, if you put this, if you imagine the Earth extending down on the other side of the Earth, the satellite can't be in direct contact. If you put the tracking station right here, the satellite can be. So if you think about where would the tracking stations need to be and how would I represent maybe the line of sight from the satellite to the tracking stations? If you got an idea, pause the video, record it, maybe draw a picture to represent that. That would be too cool. And see if you can make predictions about what's going on before I tell you. So, okay, so the line of sight would actually be something like this, and boom, just tangent to the surface of the Earth. And then over here, the same thing. And if we're looking at the Earth as a sphere, this would be symmetric. So I'm trying to draw it roughly. I'm trying to draw it well, but it doesn't come out perfect. So here it is. So this is the line of sight. If it's any further beyond this, the satellite won't be able to be in direct contact with the tracking station. So anywhere between here. So we would like to know this arc length. So let's start by saying, well, if I need this arc length, I need the measure of the central angle. So pause the video, see if you can draw that central angle. If you don't, just keep it rolling. So here's 2 radii, and I need this central angle. I know the radius of the Earth is 3,960 miles. Let me put my units. And I know, we've got a tangent, radius, point of tangency. We're looking at 90 degrees. So I've got a right angle, another right angle over here, but I just really only need to look at half if this is indeed perfectly symmetric. So let's call this angle theta. Okay, and we're going to want 2 thetas in order to determine the arc length, or I could find this arc length and multiply it by 2. It doesn't matter. So what would I do? What would I do to find theta? It's another opportunity for you to stop the video and figure out what to do next. And if you've kept it running, let's look at this. We'll say, okay, if I have perfectly symmetric, there's theta on that side, and I know this length, and I know the hypotenuse. So I know the adjacent and the hypotenuse. Then we must be talking about cosine. So I know that the cosine of theta is equal to adjacent over hypotenuse, 3,960 plus 200. In order to find the angle, I have to use inverse cosine, or second cosine on your calculator, but inverse cosine. And if I add 200, I think that's what I get. Oh, I want to close my parentheses. So that's how I could find theta. That's a plug it in the calculator thing. So very cool. Inverse cosine, I get 17.8 degrees approximately. And I want to use the exact value. I got enough error, I got enough rounding going on here that if I can use the exact value as much as possible, that would really help. So here I've got the length of arc AB, remember, is going to be 2 theta. I want that whole angle over the whole possibility, 360 degrees. That's the portion of the whole, and we're using this in degrees, times the whole circumference of the Earth. We're not looking at sector area, we're looking at an arc length. So I want 2 pi times the radius. And then I plug it in. That'll be the length of the arc, and that'll be the distance between the tracking stations. And what'd you get? I hope you got something similar to what I got, almost 2,500 miles. So this is what your calculator will spit out. But we did a heck of a lot of rounding in there and approximating. So I thought I think it's appropriate to round to even to the nearest hundred. So 2,500 would probably be better. But that's the process. So I have 2 other problems for you to do for this video. One is find the distance between the tracking stations if the satellite is 175 miles above the Earth, a little closer. How would you do that? It's the same problem, it's just with different numbers. So that's a good way of checking, do you know and understand, and are you following it? The second question is a satellite makes 1 revolution every 90 minutes or 1.5 hours. How fast is it traveling? In miles per hour. Find miles per hour because that's pretty cool. It's going pretty quick. And just so you could check your work, I've rounded to the nearest 100 miles. I've also done some rounding here, miles per hour. And yeah, there are satellites that travel that fast. They do circumnavigate the globe, the Earth, in 90 minutes. Cool. I hope it's cool for you.